Rotating detonation combustion is a promising technology for achieving pressure gain combustion and for improving combustion device efficiency. The combustor design is composed of a simple annular combustor and a detonation wave propagating around the perimeter. Reactants are injected at the head end and products exhaust to produce thrust or drive turbo machinery. A cross-section of the device is shown in the figure on the top right, where air and fuel are injected separately and where the flame is stabilized at the head of the combustor. A common diagnostic in RDC research is to visualize the propagation of the detonation wave using high-speed video. We accomplish this by imaging the aft end of the device through a mirror. In this video, we show a typical combustion test, demonstrating the high flame velocity, power density, thrust, and heat load that is common in RDCs. Through this process, we have recorded several different distinct operating modes. The standard, or canonical mode, is composed of a single combustion wave rotating at a constant speed. However, we will often observe the presence of one or more weak waves rotating in the opposite direction to the primary wave. These waves are often easiest observed when they interact with the primary wave. Additionally, they often propagate at a slower velocity than the primary wave. Lastly, an also commonly observed mode is a clapping or standing wave, in which two counter-rotating waves propagate at the same speed. In this work, our objective is to develop the tools to extract key dynamic features from the operation of this combustor with a limited number of degrees of freedom. We would like to do this using the method of dynamic mode decomposition. We begin with the simplest case of a single rotating wave. For simplicity, we parameterize and average the flame luminosity as the flame propagates around the perimeter of the combustor. In so doing, we end up with a simpler 1D measurement. When we apply the DMD, we end up with more than 400 singular values for this dataset. In order to reduce the degrees of freedom, we can truncate the results and proceed using only a much smaller set. The resultant eigenvalues for both the untruncated and truncated cases are shown on the bottom. In the plot of the eigenvalues for the truncated case, we can see the dominant modes distributed around the unit circle. Following this procedure, we can complete the DMD using the truncated set of modes. We can then try to reconstruct our original dataset using only these selected modes. However, care must be taken, such that the truncation process is not too severe. For example, one can compare the original signal with two examples, where 25 modes are retained, and also where only 7 modes are retained. This process will fail, however, when the original dataset includes a standing wave, since the DMD is unable to characterize standing waves as a complex conjugate pair. In order to get around this problem, we can use an approach recommended in the literature. To demonstrate, let's consider the standing wave case previously shown. Following the same procedure, we can reduce this dataset to our one-dimensional domain. The Ritz plot of the resultant eigenvalues demonstrates how the DMD fails. The plot shows that the eigenvalues no longer fall on the unit circle, indicating significant dampening of these modes. Following the method of Tu et al., by recasting the original snapshot matrix to include subsequent frames appended to the vertical snapshot vector, we can effectively increase the state space vector. This allows the DMD to properly capture the standing wave. By increasing the number of frames appended to each frame in the sequence, the result is improved. This allows us to better reconstruct our original sequence using the reduced set of only 25 modes. Here, one can see that the reconstruction of the reduced set with 10 additional frames appended does a better job retaining the sharp features of the detonation propagation than the reconstructed set using the same 25 modes, but without this method of appending frames. In conclusion, it appears that the DMD can be a useful tool to identify the dominant features in preparation for a reduced order model. However, care must be taken to ensure the truncation process is not overly severe. Additionally, we recommend the process developed by Tu et al. For appending subsequent frames as an effective way to better handle standing wave cases in the RDC. Thank you for your attention, and for further information, we would direct you to our existing paper on using the DMD in the RDC.